evaluate the integral of 4 minus x squared to the 3 halves, all divided by x to the 6th, from x equals 1 to x equals 2. The first thing we have to do is make sure that we choose the correct trig substitution and the correct value of a. Now, there isn't an official square root, but this is a radical, and so it's of the form a squared minus x squared, where the a value is 2. And when you're in that form, you need to go with x equals a sine theta. In this case, x equals 2 sine theta. So then after you do that, you just need to recognize what needs to be subbed for. And then you should plug in the substitution to get that expression in terms of theta. There are 3 different terms. There's dx, there's x to the 6th, and there is 4 minus x squared whole quantity to the 3 halves. We have to sub for these. The substitution is x is 2 sine theta. So you take the derivative to get dx. Dx should be 2 cosine theta d theta. Now when it comes to the root, the 4 minus x squared, you can do a shortcut. You don't have to do this, but it saves you some time. Instead of plugging x equals 2 sine theta into the root, whenever you have x is a sine theta, the root becomes a cosine theta. Just to save yourself maybe 30 seconds, a minute, however long it takes for you to do that algebra. But we don't have a root per se. Our root is actually the root to the 3rd power. But we can easily just sub in 2 cosine theta and then cube it. And what we'll have is 8 cosine cubed theta, taking the place of that part of the numerator. So both of these together make up our numerator. The denominator is x to the 6th. And so 2 to the 6th is 64. So we're talking about 64 sine to the 6th. If it's a power of 2, then it's okay raising that to the 6th. But anything 3 or 4 or anything else, you shouldn't really have to raise those to those powers. The problems should be to the point where they would have things cancel out for you. So now we have the numerator and the denominator. We are ready to plug everything back in and integrate in terms of theta. We have an 8 cosine cubed and a 2 cosine in the numerator. And then our denominator is 64 sine to the 6th. So the 8 and the 2 is 16, and 16 goes into 64 4 times, so we can pull the 4 out. But as far as the trig goes, nothing cancels. We have cosine to the 4th in the numerator and sine to the 6th in the denominator. And the whole trig power section isn't really about when they have fractions. It's about when they're multiplied or when maybe only one of them is present. And so this is a place where you could definitely get stuck. Okay. There's not much you can do. You don't want to switch into other trig functions. What you can do, though, is you don't want to use trig identities here either. The fact that you have cosine to the 4th, you want to have also sine to the 4th. Maybe you can pair that up and it becomes, cotan. And so let's try that out. Let's take sine to the 6th and make it sine to the 4th times sine squared in the denominator. Because then we'd have this cosine to the 4th over sine to the 4th. That's cotan. I know we're not used to, dealing with cotangent, but, and then this guy is the reciprocal of sine squared, which is cosecant squared. So we're looking at cotan to the 4th, cosecant squared. But this wasn't really on our powers section when we looked at trig powers. We didn't discuss cotan and cosecant, but there is something nice that does happen though, because the derivative of cotangent of theta involves cosecant squared of theta. In fact, basically, this isn't going to be exactly du, but for the most part, it'll be negative du. And so we're set up to basically just do a u substitution and be done. So let u be cotangent of theta, then the derivative is negative cosecant squared on theta. So negative du is going to take the place of this cosecant squared theta. What about this guy, cotan to the fourth? Well, if u is cotan, then we're talking about u to the fourth. And so there we have it. We're integrating negative 1/4 u to the fourth. Now that'll be u to the fifth over 5. And the negative 1/4 will multiply that. So we're talking about negative 1/20th of u to the fifth. And u is the cotangent. So we have performed the integration. And now we have to make a choice. We need to decide whether we should limit switch or not. Let's go ahead and take a look at that. So x is 2 sine theta, and that got us into this after integrating. We have integrated already. The original integral is there. I recommend taking a step down the limit switch road and see how bad it is. If you get angles from the unit circle, I say stick with it. It's my advice. So what are you going to do? Taking a step down the limit switch road is for you to plug the original x bounds into the substitution to get the theta bounds. So first up, x is 2, the upper limit. You plug that into your substitution, 2 sine theta, and you get 2 is 2 sine theta. That means sine theta is 1. That happens at pi over 2. That's reasonable. The lower limit is 1. Plug that in. You get 1 is 2 sine theta. And that sine theta is a half. But that's one of our known unit circle angles that we often use. The sine is a half when theta is pi over 6. So because we are getting these, angles that we can easily read off the unit circle, then my advice is to stick with it. And plug in pi over 6 and pi over 2. I know we're not too familiar with cotangent of theta. And so if we want to, I would just replace cotangent with its cosine and sine version. Cotangent is the reciprocal of tangent, and tangent is sine over cosine. So cotangent is cosine over sine. And we're going to plug in. Let's take a look. Let's work on the side here and figure out some of these calculations. What exactly is the cosine of pi over 2? It's going to be 0. So that being in the numerator, we don't have to worry about the upper limit. Now how about pi over 6? The cosine of it is root 3 over 2, while the sine of it is a half. And we're dividing these two guys, root 3 over 2 over a half. It'd be like multiplying root 3 over 2 times 2. These guys would cancel out. You just get root 3. Okay, so the lower limit gives you a root 3, but don't forget, you have to take that to the 5th power. So how do you take root 3 to the 5th power? My recommendation is just write out 5 of them and multiply it out. Every 2 of them will give you a 3. So you'd have a 9 outside. So the result of taking root 3 to the 5th would be 9 root 3. We have the negative 1 over 20. And then we have the upper limit of 0. And the lower limit giving us 9 root 3. And it's going to be minus the minus that would cancel to give us positive, and that would be our answer, 9 root 3 over 20. Just in case you're curious, let's take a look at what the non-limit switch would look like. You have to resort to the triangle. How do you get the triangle? You have to go back to the original substitution. X is 2 sine theta, and you solve for the trig function. Sine of theta is x over 2. And this is going to be directions on how you're going to create the triangle. Because sine is opposite over hypotenuse, you need to draw a triangle, a right triangle, with theta as one of the base angles, and the opposite side is x, and the hypotenuse is 2. That's where the triangle comes from. Now to get the third side, just use the Pythagorean theorem. Most times it's going to be the root that got you in the first place, but sometimes there's not even a root involved, or there's a 3/2 power like what we have. So just do the Pythagorean theorem. Leg squared plus leg squared is hypotenuse squared. So 4 minus x squared underneath a root should be what the third side is. And remember now, we're looking at the cotangent of theta that needs to be raised to the 5th power. And cotangent would be the reciprocal of tangent, so it would be adjacent over opposite in the triangle. So it's going to be this root of 4 minus x squared over the opposite of x. This is the guy we need to raise to the 5th power. And we can then use our original x values of 1 and 2. And don't forget about the negative 1 over 20 outside as well. So we put a 2 in, and what happens? 4 minus 2 squared, that's 4. 4 minus 4 is 0. So upper limit gives us that same 0 that we got from the limit switch. What about the lower limit? You put a 1 in, and you get 4 minus 1 underneath a root. That's a 3 underneath a root, and that's our 3 to the 5th that we got before. The denominator is just a 1 there. And so we end up with exactly the same answer. That this guy here is 9 root 3. So we end up with 9 root 3, 20. All over 20 for our final answer.